This is 1.3 part 2. We're starting with example 4 of 6. So again, we have a piecewise function here. We're going to evaluate the limits exist. We're going to look at going to 1 and going to -1, because those are my breaking points. I have a break point right here at -1 here, and then 1 and 1 here. So the first one, let's go ahead and look at 1. So we're going to, in order to do this, just like we did in our warm-up, we have to approach 1 from the right, okay, and we have to approach 1. Oh, writing's getting bad. Okay, or worse. Approach 1 from the left of f of x. Okay, and again, we're approaching from that direction. That'll put us into one of our pieces. So let's see. What do you think, Rachel? If I'm approaching 1 from the right, what piece does that put me in? X squared minus 2x. So I'm going to put a 1 in. 1 squared minus 2 times 1. Okay, which gives me what? Good, -1. Okay, if I'm approaching 1 from the left, where does that put me, Garvey? Which piecewise? The x. So it'd simply just be 1. I just plug it in for x. So I get 1. These right here, what's that mean? D and E does not exist because I have different limits coming from right to left. That's because the question asked that. You'll be given what you're taking a limit of, because this part's given. Okay, now we're going to look at -1. Okay, so we're going to look at -1 from the right, and we're going to look at -1 from the left. Okay, of f of x. So Emily, if I'm doing -1 from the right, what piece does that fall me into? The x. Good job. So I would put -1 in, so I would just get -1. Okay, and then Rye, if I was approaching -1 from the, wait, did you do to the right? Yeah, you did the right. What, if I approach -1 from the left, where would that put me? Nope, from the left. Because where would, like, the left side would be less than, right? So then it would be this one. -1, negative, -2. So minus and minus is a plus. 1 minus 2 is -1. So these ones, they did match. Okay, so that means it exists. That is the limit. The limit is -1. Good. So exists. Okay, good. Okay. All right, so let's get to the next page here. All right, so discontinuous. Just to further, we already kind of talked about this enough, but I think I spelled that right. Discontinuous, okay. F is continuous. A number A if x can go to A, like if you could put in that limit. 3 things are required for this to be true. Okay, so these are the 3 things we look for continuity. We kind of already know 2 of them. Okay, the first one, f of A is defined. So that means that when I plug in what I'm taking a limit of, it's defined. Okay, so if it's not defined, then it's going to be discontinuous, or we can't take the limit, so it's not possible. Second thing, in order for to have continuous, that has to happen. These 3 things are all required. Three required for continuity. Okay, limit as x approaches A of f of x exists, so the limit exists itself. Yeah. Yes. These 3 things need to happen in order to prove continuity. Yeah, if it doesn't have a limit, then it is discontinuous. Yeah. I guess that's the best way to answer your question. Okay. And then the third and final thing, which we've already done, limit, this is the one that you guys know, limit as x approaches a of f of x needs to be equal to f of a. So just plugging a in for x, it is continuous. So, I guess, wait, let me correct that. So, Emily, can we have something continuous that's not a limit? Yeah. Wait. Yes. Wait. No, actually, this is what I mean. If we have like a line, right? Let's say I put an open dot right here. I meant to say, can we have discontinuity and then have a limit? That's what I meant. We can, because right here being an open dot, like the limit, they approach the same number, right? They approach the same number, but the open dot still stops the continuity. Okay, the open dot stops the continuity. I guess that's the best way to think about it. But don't worry about that. I was just trying to see. Right, that's what I'm trying to say. Yes, that's what exactly right. Sorry if my picture is horrible, but we will continue on this. But I was trying to answer more what Emily was saying, because what I'm trying to say is these things need to happen for continuity, but you can have a limit without continuity. That's what I'm trying to say. Okay. Next thing, so example 5. So where are the following functions discontinuous? So we're trying to figure out where these are discontinuous. Wow. Let's try this again. Here. Wow. I like heads in my hands like dead. Alright. Alright, there we go. Okay, so x squared plus 1, x less than 0, 0, just 0, at x equals 0, and x squared minus 1, x greater than 0. Okay, so what we're going to do is we're going to look at the limit. Now, so this is going to be an example of, so let's just kind of graph this just real quick. So x squared plus 1, so that means I'm going to be up 1, and it's less than 0, so it's going to be open dot, and then we want less than 0 for that one, so it's going to be here. That's this guy. Okay, x squared minus 1 would be down here. Again, it's open dot. Okay, and then it's going to be up 1 over 1, so it's going to be like here. And then x equals 0 is just a dot at 0. It's right there. That's what that picture looks like. Okay, so right now, look at that picture. What's your intuition say in terms of what's going to happen with your limit? It's going to be discontinuous because they don't converge to the same number. This guy is converging to 1. That's at 0, and that's at negative 1. Okay, but let's go ahead and do it here. So what we're going to do is we're going to limit as x approaches 0 from the left. Why are we picking 0, like Jeremy asked earlier? Because that's our breaking points. That's where we're changing. Yep.
When the function is just x equals 0 to 0.
Yeah. Yep.
And that's why on the last one, like our two breaking points are negative 1 and 1. That's what we both do.
Yep. Okay. So limit as x approaches 0 from the left. So as x approaches 0 from the left, we are going to be using this guy because that's the left of 0. Okay. If I plug 0 in, I get 0 squared plus 1. I get 1 for that limit. Now if I do limit as x approaches 0 from the right, I will get this guy because that's bigger than 0 coming from the right. So I'll be coming from here. Okay, so I'll put 0 squared minus 1. I get negative 1. Not the same D&E. The limit does not exist. It's discontinuous. Okay. Okay, so let's look at the second one here. This is a part B of example 5, and then we have example 6, and we're done. So part B, we have x plus 1, 1, x can equal 2, x equals 2. So, this one's kind of interesting. So what this means is, what this picture would look like, you have at 1, x equals 2. So we're going to be at 2. We're like right here. It's just a dot by itself. That's what this is. A dot at 2, 1. Okay. This one is going to be everything x plus 1 except for 2. So x plus 1 starts here. It's going to go up 1, over 1. Up 1, over 1, but I can't do this one, so it's going to be open right here. And then it just keeps going. These two are directly above each other. I know my picture's a little off. That's kind of what the picture looks like. Okay, so limit, what we're going to look at is limit as x approaches 2. Okay, as limit as x approaches 2 for this one, because as limit approaches x is 2, I'm just going right to here. Well, it's just the answer's 1. Okay, there's nothing I put in, so I would just get 1. Yeah, exactly, because of constant. And then limit as x approaches 2 for the other one, because this one can approach 2 from the right and the left still, so we can still evaluate that one. And so this one would be 2 plus 1, which is 3. So these are different, so we get discontinuous again, does not exist. And this is where I was kind of talking about. It's just open dot, but the solid dot's down here, so it's discontinuous. It's not one nice fluid thing that's out of the way. All right, last one. I got to go back to page 1 for that. I like the last example because this is realistic. We're doing stuff with, like, phone companies always round up your minutes. So if you talk for 36 seconds, they still charge you for that next minute. So this is similar to that. So it says the cost of long-distance nighttime phone call from Pine Bay to Hester is 26 cents for the first minute and 22 cents for each additional minute. There's a minimum charge of 34 cents no matter how long you talk. And draw a graph of the cost of C in dollars of a phone call as a function of time in T minutes. Where are the discontinuities of this function? So where is it discontinuous? So what we're going to do is first we're going to develop our functions, get an idea what's happening. So our first C of T, okay, how much does it cost to talk for 0 to 1 minute? Starts at what? The 34? Yeah, starts at 34. So because it says every minute is 26 cents for the first minute and 22 for each additional minute, but if you just talk for 1 minute, you get charged the minimum. The minimum is 34 cents. So C of T for 1 minute is 0.34. This is for T greater than or equal to 0, less than or equal to 1.
In your class change.
For 1 minute. Okay, how much does it cost between 1 and 2? So bigger than 1 but smaller than 2. 48 cents, right, because now it's 26 plus the 22, because they always round up on you, so you're going to have to pay 48 cents. So we'll write that as 26 plus 22. That's C of T. Yeah, sorry. 48 cents. So then we're going to do, yeah, Emily? No, because the 34 is kind of a fallback. So the 34 only comes in if you pretty much just talk for 1 minute. Because 26 plus 22, is that bigger? It's bigger than 34, so you won't get that 34-cent charge. Yeah. It's pretty much just saying if you talk for 20 seconds, they're going to charge you for 34 cents no matter what. Yeah, well, that's what phone companies do. I mean, they have a minimum charge for phone calls. Okay, so yeah, we're over the minimum, so that won't happen anymore. So C of t, now if we go from 2, not equal to, sorry, 2 to 3, okay, it's going to be 26 cents plus 2 times 22. It's going to give us 44.70, 70 cents. Okay, and the last one that we're going to do is between 3 and 4. So C of t, 26 plus 3 times 22 equals 92 cents. So this is a step function where it has discontinuity every minute, okay, because it's a jump. They don't charge you per second, so it's not like a gradual continuous function. These are called step functions. So what this looks like, just to give you a little picture here, so X is our minutes, right? Our T. I should put T's there. I guess I switched them. But T, so we did to 4 minutes, 1, 2, 3, 4. Okay? So if we did money here, let's do, let me go up by 10 cents. I probably should go by more than that, but. Okay, whatever. So all that's 90 cents. Okay, so my first charge, so between 0 and 1, what should my line look like? What's that? Straight line at 34. So 34, yeah, 34, it's going to go here to the 1 here and have an open dot here. Because as soon as you hit the next minute, what happens? As soon as we hit over 1 minute, it's going to be 48 cents. So actually, sorry, it could be solid here. It's going to be open on top of that, sorry. So the next one is going to be up at between 1 and 2, but it's going to be 48 cents. So it's going to be here to there. And that's why they call a step function. This is like step 1, step 2, we're going to keep stepping up. Yep. Right, so should be, no, you're right. So I had it right, didn't I? I think you're right. I mean, this is open, that's closed. Yeah, you're right. Open, closed, that should be open. Let's see here. So we said 0 and 1 is equal to for 34 cents. So if it goes, because as soon as you talk for 2 minutes, no, you should be in this one. I think I have them marked wrong. I think I have marked wrong. So Austin, you're right, but I should have it marked this way. Because I know that's how mine doesn't make sense to what they're charging. Because as soon as you, like she just said, as soon as you hit 2 minutes, you're going to be next in the next bracket. You don't get the second minute. Does that make sense? Okay. All right. 70 cents is my next one. So I'm right here. We're going to go up to here. So close dot. And then we go to that for open dot. And our last one of 91 or 92, it's way up here. So there's your step function. Okay, so where are the points of discontinuity? At every minute. Okay, at 1 minute there is, 2 minute, 3 minute, 4 minute. Because breaks, jumps, breaks, jumps. That's your points of discontinuity. Okay, and that's it.